So basically we are discussing about the fuzzy logic controller. So this will take a crisp input, and this crisp input will be converted to a fuzzy value through the fuzzification module, and this will be processed by the fuzzy inference engine using fuzzy rules. And this fuzzy inference engine, basically this is the one which is going to produce the output, but the output will be a fuzzy output, but in most cases the real world wants the output in a crisp form. So this fuzzy output will be given to a defuzzification module, which will convert the fuzzy output to a crisp form, and then it will be sent to the real world. Okay. So this is the, so this block is the, so this entire thing is the fuzzy controller. So you can see here, so this fuzzy controller, it includes several blocks. It includes the fuzzification module, it includes the defuzzification module, it includes the fuzzy inference engine and fuzzy rule base. Okay. So how this fuzzy controller, fuzzy, you can call it as fuzzy controller or fuzzy logic controller. So how this fuzzy logic controller is designed, that is what we are going to discuss in today's session, right? So these are the components of a fuzzy logic controller. It includes the rule base, inference engine, fuzzification module and defuzzification module as shown in this diagram. Okay, this entire thing, right? Okay. Now there are so whatever we have discussed it there, that's what explained here. Now there are two ways to implement the fuzzy logic controller. There are generally two approaches are available to implement FLC, which is nothing but fuzzy logic controller. One is called as Mamdani approach. The other one is called as Takagi and Sugeno's approach. The first method is Mamdani's approach. The second method is Takagi and Sugeno's approach. The first method actually it builds an fuzzy controller, fuzzy logic controller, which is less in accuracy but which has high interpretability. So interpreting in the sense how it is working, you can analyze that. So that is called as interpretability. So Mamdani approach provides less accuracy but it is highly interpretable. Whereas Takagi and Sugeno's approach, it provides an highly accurate fuzzy logic controller, but it is less interpretable. Its interpretability is less. Okay. So actually you cannot ignore this interpretability feature. This is also one of the important feature in case of artificial intelligence or machine learning or whatever it may be. Okay. So fuzzy logic, so the entire subject whatever we are discussing, soft computing, it's actually one part of artificial intelligence. So in artificial intelligence it is not just producing output, but interpretability is also equally important, like why the system is producing this output, why it is behaving this way. So it's not that just okay, as long as it is providing good output it is fine. No, it's not that way. Interpretability is also a serious issue. Okay. So if you see these two approaches, Mamdani approach provides less accuracy but more interpretable, whereas Takagi and Sugeno's approach, it provides it is highly accurate but is less interpretable, right? So if you are aware of deep learning systems, so deep learning systems are highly accurate but they are less interpretable. So that is one of the critique on that particular way in which the deep learning system is working, right? Okay. So now we will be discussing the Mamdani approach by using an example. So this example what we are going to discuss is called as a mobile robot. So here we will have a mobile robot. So this is the robot, and this robot will be moving in a particular area. This is the given area. But apart from this robot, here there are four objects are there. O1, O2, O3, O4. These four objects are there, and each of these objects were moving in different direction. So you can see O1 is moving in this direction, O2 is moving in this direction, O3 is moving in this direction, and O4 is moving in this direction. Now the robot is also moving in this direction. Okay, now the robot should move in such a way that it should not collide with any of the objects. It should not collide with any of the objects. Suppose if there is a chance of getting collided, then the robot should change its direction. Okay. So here we are going to consider three parameters. One is called as d, which is distance. The other one is angle, which is represented as theta. The other one is deviation, which is represented as delta. Okay. So these are the three parameters we are going to consider here. D, which is the distance, and angle, which is theta, and deviation, which is delta. So D represents how far the robot is away from an object. Okay, so that is called as D. So for example, the distance between the robot and a particular object, that is D. So the distance between a robot and this O3 is D. Similarly, distance between any other object, that is called as D, right? And theta is the angle between the object, the angle between the object and the robot. Okay, so object is moving in this direction, right? And the distance between a robot and object is this. So this angle is nothing but theta. This angle is nothing but theta. Okay. Okay. Now what is delta? Delta is deviation. So deviation, what it says in the sense, if there is a chance that a robot may clash or collide with any of the object, then to avoid the collision, how much it should deviate. How much it should deviate. So in this case, for example, if the robot is following this path, then it is highly likely that it may collide with the object O3. So it should deviate. So it should either deviate its path, either it should go in this direction or it should go here. Okay. So how much deviation it should take from its original path. Okay. So this, whether it should go, it can take either this way or it can take this way. So this angle of its changing its path, so that is called as deviation. Okay. So these are the three parameters we are going to consider: d, theta, and delta. So d is the distance between robot and any given object, and theta is the angle between the robot and the object. That is, actually it is the distance between the robot and the object, and the object in which direction it is moving, the angle between that. Okay, so that is theta. And deviation is how much the robot should deviate from its path so that it will not collide with the nearby object. Okay, so basically we have to calculate delta. So basically we have to calculate delta. Okay, so you will be given d and theta, so you have to calculate delta. So that is what this problem is all about. So how we are going to do this with Mamdani's approach, that's what we are going to discuss, right? So we consider two parameters. These are the input parameters: d, the distance from the robot to an object, and theta, the angle of motion of an object with respect to the robot. Okay, the angle of motion of an object with respect to the robot. The value of these parameters with respect to the most critical object will decide the output called deviation. So output is deviation, that is how the robot should deviate from its path. Okay, so based on these values, this should be decided, right? So let us assume that d takes values between d takes value in this range 0.0 to 2.2. That is, this is the smallest distance possible between a robot and an object, and this is the maximum distance possible between a robot and an object in the given area. And this is the theta, that is the angle between the angle of motion of an object with respect to the robot, can take any one of these value, minus 90 degree to plus 90 degree. Okay, right? So Mamdani approach basically it uses linguistic states. So what is linguistic states in the sense, for example, distance. So distance, now we can here we are representing numerically 0.1 to 2.2. For example, 2.2 we can say it is very far. So this is called as linguistic, because linguistic means it is what? It is like a English like or some human language like approach. So instead of saying 2.2, we will say very far. If it is 0.1, we will say very near. If it is 0.1, we will say very near. Okay. Maybe if it is 0.3 or something, then we will say near. So this type of representation is called as linguistic representation. So for example, if it is 0.3, then it may be near. There may be some value for far also, right? So so whatever the distance, the value will be mapped to appropriate linguistic notation. Okay, right. Similarly, this degree also will be mapped to some linguistic notation. Okay, so Mamdani approach is to select some meaningful states called linguistic states. So all these things will be represented using linguistic states. So here is the linguistic states for distance. So distance is represented through these linguistic states. Okay, so actually these are the actual distance available, 0.1 to 2.2 meters, and these are the actual angle or degree, angle possible, angle of I mean the angle of motion of an object with respect to the robot. So these are the possible angles between the object and the robot is possible. But again Mamdani's model expect that these should be represented in linguistic notation. So this is how the distance is represented in linguistic form. So these are the various linguistic states we are using. Vn, which stands for very near, Nr, which stands for near, Vf is stands for very far, Fr is stands for far. Okay, so these are the four linguistic states which represents the distance. Similarly, angle. Again, here we have two types of angle. One is theta, which is the angle between the moving object and the robot, and the other one is the delta, which is the deviation, which is the output angle, which is the deviation the robot should take from its current path to avoid collision. Okay, so both these angles, theta and deviation, can be represented using these 5 linguistic states. So these are left. So that means it should go towards the left, or the object is towards the left. Okay, and ahead left. Okay, this is straight left. For example, robot is here and the object is here, means so this angle is something like that. Okay, so this is called as left. Okay, ahead left means robot is here, object is here. So okay, so this is left, ahead left. Okay, ahead means straight. So robot is here, object is here, then it is ahead. Okay, similarly ahead, right and right. So these are the 5 linguistic states which we use to represent the angle. So there are two types of angle. One is theta, the other one is delta. Theta is the input, which represents the angle between the object and the robot, and delta is the deviation, which is the output. That is how much the object should be, how much the robot should be deviated to avoid collision. Okay, right. So these linguistic states are represented using this graph, right? So these different fuzzy sets for 3 different parameters are represented below. Okay, so this is for distance. So distance is represented through this, and this is for angle of angle in degrees, and this is deviation in degree, right? So you can see here. See, this is Vn. So Vn is represented using this membership function, very near. Okay, so this represents very near. This represents near. So this membership function, it represents near. Okay, this thing, it represents near, right? And this is very far. Very far is represented like this. Sorry, far. This is far. Far is represented like this, and very far is represented like this. Okay, so this is how they are represented, right? So of course there will be what you call there will be some places where 2 or more member functions will may occur. So that is what the nature of the fuzzy logic is. Okay, so fuzzy logic will always allows that. So if it is only a crisp logic, will not allow that, right? For example, if you take this particular point, okay, so if you draw a line here, so it means that it has some, say for example, it has a membership value of 0.2 corresponding to near. Okay, and it has a membership value of 0.8 corresponding to very near. Okay, so it is coming in the class of very near, and also it is coming in the class of near. So for near it has a membership value of 0.2, for very near it has a membership value of 0.8. Okay, so that is fine, that's okay. So that is the nature of a fuzzy system, because that is how the fuzzy works. Okay, so this is the basic characteristics of a fuzzy system, right? Okay. So that this what do you call this they 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 share values between certain ranges. Okay, for example, very near you can see it is between this 1 and 0.8. Okay, when x value is 0.8, its membership value is 0, right? Okay, when x value is 0.1, it's 1, right? This is like that, right? Similarly, this is angle in degrees. So this angle in degrees, if you see, so this is LT. LT is represented like this. Okay, so if you see here, LT means left. LT means left, so it means the object is to the left. Okay, and this is AL, ahead left. Ahead left is represented through this membership function. This is AA, this is ahead, this is just ahead, which is represented like this. This is ahead right, which is represented like this. This is right. Okay, so the same membership function which we are using for angle, the same thing we are using for deviation. Okay, so only thing is the angle represents the angle between the object and the robot, and deviation represents the how much the robot should be deviating from its path, so that there will not be a collision. Okay, right? So these are the linguistic notations we have. So we have for distance we have 4 linguistic notations, and for angle we have 5 linguistic notations. Okay, now if you see, it can be any combination may happen. The robot, the possible situation the robot may face is, it can be a combination of anything. For example, the robot may encounter an object that is very near and which is to the left of it, or it may be very near ahead left, very near ahead, very near ahead right, very near right, like that. Or robot may encounter a situation like near left, near ahead, near ahead right, and near right. So I have a question here. So like this, the robot may encounter totally how many possible situations? Is the question is clear? Totally how many possible situations the robot may have to face? See, what we are discussing in the sense, the robot should not collide with any of the object. If there is a chance of collision, it should take a deviation. Okay. So for distance we have 4 linguistic states. For angle we have 5 linguistic states. Okay. So at a given point of time, robot may encounter any combination of this. So I have given some examples, like it may encounter an object such a way that it is very near and to the left of it. The object may be here, so it is very near and left. Or it may be very near and ahead left, or it may be very near ahead right, very near right. So these are 5 combinations. With very near, all these 5 combinations are there. So like that, totally how many possible situations the robot may have to face? Yes, 20. Yeah, kilo, good. So totally there are 20 situations. Okay, so this can be represented using a matrix. So that is, you can represent this as a matrix, something like this: Vn, Vr, Vf, and Fr, and in the column you can represent all the other things: LT, AL, AA, AR, and RT. Okay, that is if this is the situation. If the object is very near and if it is to the left of the robot, then what the robot should do? That action will come here. Okay, if the object is very near and if it is to the what is called, what you call, ahead left, then what action should be taken? Like that we have to. So this is called as the rule base for this problem. So for this problem we need to identify 20 rules. So these are the different 20 situations. So in these 20 situations, how the robot should react, so that we have to fill up this matrix, right? Okay, so let us assume that this matrix is given like this. So what it means in the sense, If the object is very near and if it is to the left of the robot, so the robot is here and the object is here, so it means it's very near and it's to the left, then what the robot should do, so this is delta, what the robot should do means it should AA, it should go ahead, okay. For example, if the robot is following this path, it should go ahead, or if it is any path, it should go ahead, okay. That is what it says. Now how this is formed, we are not concerned about this. Let us assume this is given, okay. How this AA is come here, why not here AR, let us not go into that, we are really not working on that. Let us assume this is given like this. So this is the rule. So if the robot is if the object is very near and if it is ahead left, then what the robot should do means it should deviate towards right. It is robot is here and the object is here, okay. Then robot should go towards its right, okay. It should go towards its right because object is coming here, so ahead right, so robot should go here, it should go here, so that object will go like this and robot will continue, right. So like this, these rules were given, right. So here basically all these are the actions the robot should take when it encounters this situation, right. So here everything is represented in a linguistic notation. The situation is also in linguistic form and the action is also in the linguistic form. So the situations are represented through the rows and the columns, and the respective actions also represented in the linguistic form, right. Okay. So like this, so like how I said, no, so totally here there are 20 rules. So these 20 rules you can write down like this, or the system can understand there are 20 rules. That is, so what the first rule says, if distance is Vn and angle is Lt, then deviation is AA. That is, robot should deviate like this, okay, because this represents distance between robot and object. If distance is Vn and angle is Lt, then the robot should deviate by AA. If distance is Vn, angle is AL, then the robot should deviate by AR. So like that, the system will have 20 rules, okay. The system will have 20 rules, but given a situation, not all the 20 rule may be applicable, maybe some of the rules may be applicable in a given situation, right. So I think it's clear. So these are the 20 rule. Note that this rule base defines 20 rules for all possible instances. These rules are simple rules and take in this following form, okay. Now let us take one example, okay. Let us consider that, let us take a typical value for D and angle. So let us assume D is equal to 1.04 meter and angle is equal to 30 degree. That is, there is an object, so robot is somewhere here, so there is an object, okay. There is an say there is an object here, okay, and the distance between robot and the object is 1.04 meter, okay, and the angle is 30 degree. The angle is 30 degree. In that case, what the robot should do? So this is the problem we are going to address, okay, in the rest of the lecture for Mamdani's model. So the distance between robot and the object is 1.04 meter, and the theta and the angle between the robot and the direction in which the object is moving is 30 degree. For this input, we have to identify delta. That is how much the robot should deviate from its path to avoid collision, okay, right. So 1.04 may be treated as near or far. How it comes, that let us see that, okay. And theta equal to 30 degree can be declared as either AA or AR, okay. So this statement says that if D value is 1.04, it may be either in near category or far category. Theta equal to 30 degree, it can be either AA category or AR category. AA is ahead, AR is ahead, right. So how these values were achieved, in the sense, you just see this what you call this diagram, okay. So here, so this particular thing represents distance. So this is the membership function for distance, right. Okay. So this represents distance. Now what is our distance value? 1.04. Okay, so you can see here, this is 0.1, this is 0.8, this is 1.5. So 1.04 is coming somewhere here, right? This is 1.5, so 1.04 is coming somewhere here, right? So if you draw a line from 1.04, if you draw a line from this 1.04, it will intersect on here, on this line, and on this line. What is this line? This is NR. NR represents near. Okay, and what is this? FR. FR represents far. So it will have two membership value. It will have two membership value. It will have a membership value corresponding to near, and also it will have a membership value corresponding to far. Okay, so this is how we say that 1.04, if the distance is 1.04, then the object can be either, you can consider as either the object is near or the object is far, depending on the membership value that you take, depending on the membership function you consider, right? Similarly, 30 degree. So this is minus 90, this is minus 45, this is 0, this is 0, this is 45. Okay, so 30 degree means where it will come. So this in between point you cannot say as 30 degree. Okay, because 45 by 2 is, this is 0 to 45, 45 by 2 is 22.5. okay, so somewhere here 30 degree will come, right? 30 degree will come somewhere here. Again, if you see this 30 degree, it is going to intersect on these two lines. Okay, so it is taking which membership values? It can take either the member, it can come either the either under the membership function AA, if you consider this membership value. Similarly, it may also come under the membership function AR, ahead right, if it takes this membership value. Is it clear? So this is how we say that this 1.04, it will either fall under near what you call near and far, and 30 degree it may fall either under AA or AR. Okay, right? Let me give another value, say 1.7. So 1.7 means what are the possible linguistic distance it may take? Could someone answer? 1.04, it has taken, it may take either on near or far. Similarly, 1.7 means what are the possible linguistic values for distance it may take. Yeah, good, Kilo. So 1.7 means it will come here. Okay, so it means it will intercept here, and also somewhere it will intercept here. So this is very far and this is far, right? Okay, say for example, similarly, say the angle is 80 degree. So angle 80 degree means what are the possible linguistic values it can take for angle? Yeah, so 80 will come here. Okay, so it may intercept here and it may intercept here. So it may take either ahead, right, or right, depending on the membership value, right? Okay, so this is how that statement was defined. Okay, I think it is clarified now. So so what we say in the sense, for this particular value of 1.04, I mean the distance value of 1.04 and angle 30 degree, it may be, the distance 1.04 may be called as either near or far, and similarly 30 degree can be declared as either AA or AR. Okay, now but still we don't know the what you call, still we don't know, that is fine, we got some idea, but still we don't know the actual membership value. So how to calculate the membership value? So here the membership value is given, that is, if it is near, then this is the membership value. Okay, so I mean 1.04 can be either near or far. If it is near, this is the membership value. If it is far, this is the membership value. Similarly, 30 degree can be ahead or ahead right. If it is ahead, this is the membership value. If it is ahead right, then this is the membership value. Now how we got this value? Actually there is a method to calculate this. So that's what that is explained in this slide. So here you can see there is a formula. So first you see this diagram, I mean the below diagram, don't see this, see this, okay. So here, so actually there is a concept called similarity of triangles, okay. We are this is some mathematical concept, we are using that technique here. So there is a concept called similarity of triangle. So based on that technique there are some a formula. So based on that formula this is working, right. So here you can assume there are two triangles are here. See, this is one triangle, this is one triangle, and this is another triangle. Now both these triangles are similar in shape, only thing is one is larger, the other one is smaller, okay. So if you have two such triangles, okay, and now if you want to say this x we want to find, this is the one you want to find, okay. So this height you want to find, right. This height we don't know, this is the one we want to find. So we are also facing the same problem here, this point. So this is 1.04. So what is this value? We don't know. Exactly we don't know. Similarly, this value we don't know. So for calculating these things, we are going to use this similarity of triangle method, right? So if this x point you want to know, then you can apply this formula. So this formula, what it says in the sense x by y. So this x you want to calculate divided by y. Assume that this height is known. Assume that this height is known, okay. Then x by y is equal to delta 1 by delta 2. Delta 1 is the distance between this point and this point, okay, and delta 2 is the distance between these 2 points, right. So if you solve this equation, then you can find the value of x, right. Okay, so now we have to find, so we need 2 points, we need this point and also we need this point, but we have to do one by one, okay. First let us consider only this point, okay. If you consider this top point alone, then this is, you can consider this as one triangle, okay. You can consider this as one triangle and this as another triangle you can consider, this is another triangle you can consider, okay. Now you can apply this rule, right. X is the one, this is x, okay, this is x, x is the one you want to calculate. So x by, what is y? This is y. What is its height? What is its height? 1. So this is known. So you can directly write x by 1 is equal to, this is delta. This is delta 1. So what is delta 1? This point is 1.5. This point is 1.04. So what is delta 1? 1.04. 1.5 minus 1.04. Okay. This entire thing is delta 2. 0.5 to 1.5 is delta 2. Okay, so how can you calculate 1.5 minus 0.5, right? So 1.5 minus 0.5, right? If you solve this equation, you will get the value for x. So that is how we got this 0.6571, right? So now we have found the only one point, right? So that point is corresponding to what? So this is I guess this is corresponding to NR, okay? That is if 1.04, if we consider the membership function near, then this will be the value of the membership value, okay. That is x, if x value is 1.04, then the membership value will be 0.6571, okay. Similarly we have to calculate the remaining thing also. See, if you want to identify now, but actually say we want to identify this point we want. Now you have to take this triangle. Now you have to take this triangle. Okay. So this is also a triangle. So I am not getting the diagram properly. So this triangle you have to take. So this small one you have to take. Okay. So this is the smaller one. Then the bigger one will be this. This side you have to take. Okay. This is the bigger one, right? Okay. Now this is x. This is x. This is y. Okay, again what is x is x only. What is y? What is its height? What is this height? 1. So x by 1 is equal to delta 1. What is delta 1? This is delta 1. What is delta 1? What is the difference between these two? This is 0.5, this is 1.04. So what is that? So this is 1.04 minus 0.5, right? 1.04 minus 0.5 divided by delta 2. Delta 2 is this entire thing. Okay, again this is 1.5 minus, sorry, this is 0.8, right? 1.04 minus point, this is 0.8. This is 0.8. Okay, here also it's 0.8. Okay, 1.04 minus 0.8, then this entire thing is 1.5 minus 0.8. Okay, so if you solve this, then you will get this value, right? So that will be, so what will be the result here? 1.04 minus 0.8, which is 0.24. The numerator is 0.24 divided by 1.5 minus 0.8. What is 1.5 minus 0.8? It's 0.7, right? One 0.5 minus 0.8 is 0.7. So 0.24 by 0.7. What is the value? 0.24 by 0.7. Okay, 0.342, right? So this is the value for, this is the membership value for what? If it takes the value for, okay. So this is the membership value for near, 0.6571, and for far this is 0.342, right? Similarly for angle also you have to calculate. Okay, so 30 degree, actually this line is wrong, 30 degree will not come in the middle point. Okay, so you can say that 30 degree is somewhere here, so it is going to hit on both the lines. It is going to hit here and also it is going to hit here. Okay, so again we have to consider like that, right? So this is, one part. Okay, and this is another part. Okay, and like that we have to calculate, right? So like that only this is solved. Okay, so we calculated this 0.342, we got this, right? Similarly you can solve for this also, so you got 0.33 and 0.667, right? Okay, so this is how these values are obtained here. Okay, so this is how these values are obtained. So this is the first step. So we are trying to identify what, given the distance and the angle, how much the robot should deviate. But to calculate that, first you have to identify the possible membership value. Okay, because it is not going to because the input will not strictly fall under one membership function, because we are talking about fuzzy logic, so it may take more than one membership function, right? So in that context we are discussing, right? Okay, so I think this also we can try. See, this is so let us say this is 30, here it is angle given. Okay, so if it is this point, say we want to find this, so this is one, this is another. Okay, so this is the one we want to find. So this is x. Okay, so x by 1 is equal to this distance we want, so this is 30. Okay, so this is nothing but delta 1 is nothing but 45 minus 30. 45 minus 30 is 15. Okay, and this is nothing but, this entire thing is 45. Okay, so what is 15 by 45? Yeah, so that we got here 0.333, right? This value you got, right? Similarly the other way around also you can calculate. So So in the second case, what we want to do, we want to find for the smaller line. So now also 30 is here, it is going to cut here, but now we are not bothered about, we want this info, right? So you have to take this small triangle and this one, okay, and this one, okay. So this point is 30, right? Again x by y is equal to, so this is delta 1, okay. So this distance is 30, 30 divided by this distance is what, 45 minus 30, this is x by 1, right? 45, no, something wrong. Okay, so actually this line will be here, this will be more than the middle point, so it will be somewhere here. Let us assume here, okay. So 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 this is the smaller triangle and this is the larger one, okay. So this is this height we want, so it is x by 1 is equal to, this distance is what, this is 30, okay. This is delta 1, right? Now this is delta 1, this is delta 1, and this is this entire thing is delta 2, entire thing is delta 2, right? So yes, so this is, sorry, this is delta 1, this entire thing is delta 2, so it is, I think it is 30 by 45. What is 30 by 45? Yeah, so that is how we got this value, right? Okay, so this is how we solve this, right? So this is how we find these values. So don't miss the flow. So given, so what is given, distance is given as 1.04, angle is given as 30 degree, that is the that is how the object is separated from the robot. Now we have to find like how much the robot should deviate from its path to avoid collision using Mamdani's approach. But before going ahead, first we have to find all these values, okay. So why we are finding this, in the sense we have to find what are the possible rules that will fire. If you recall, there are 20 rules, we have 20 rules, but not all the 20 rules will fire in all the cases. So depending on the input, so for this input, that is if the distance is 1.04 and angle is 30 degree, then how many rules will fire? Okay, so in this case we have, these are the four options available, okay. So any combination of these four can happen, are you getting? Any combination of these four can happen, okay. That is, for example, the object may be near and it may be ahead, this is one combination. Or the object can be near or it can be ahead, right, this is another combination. Or the object can be far and ahead, this is another combination. Or the object can be far and it can be ahead, right, this is another combination, okay. So for this given input, how many combinations of situations are possible? Four combinations, yes, good. So with near it can be ahead and ahead, right. Similarly with far it can be ahead and ahead, right. So there are, again for this input there are four situations possible, okay, because that is how our fuzzy relations were defined, right. Okay. So these are the four cases. So now these are the four possible rules it can fire for this input. So totally the rule base, if you see, it contains 20 rules. But now in our case all the 20 rule will not fire. Any one of these 4 rule will fire. So what is the rule? NR. So first combination, if you see, it is NR and AA. Then NR and AR. If it is NR and AA, then what should be the result that you can see here? So this table gives the full rule database, right? So if it is NR and AA, then what should be the deviation? So if it is NR and AA, then the robot should deviate towards right. Okay, right. It should go towards the right. Okay. If it is NR and AR, then the robot should go ahead. Okay, right. Similarly, far. If it is far and AA, then the robot should go ahead right. Okay. If it is far and AR, then the robot should go ahead. Okay. So in our case, these are the 4 possible combinations, nothing else. Okay. So that rule alone we are finding out. So what are the rules will fire for this given input? What are the rules may fire? So these are the 4 possible rules. So we are just writing out R1, R2, R3 and R4. That is, if distance is NR and angle is AA, then deviation is RT. Okay, it is towards the right. If distance is NR and angle is AR, then the deviation is AR, ahead. Okay. If distance is FR, far, and angle is ahead, the deviation is AR, ahead, right. If the distance is far and angle is ahead, right, then the deviation is ahead. Okay. Right. Now we are going to now again we are going to identify the strength of each rule. Okay, so these are the possible 4 rules. Now we will find the strength of the each rule, so that we can ignore the rule which with lesser strength. Okay, and we will take the rule with more strength. Okay, so how we are going to calculate? So we are going to calculate the strength of each rule. Alpha represents the strength of a rule. So alpha of R1 is equal to minimum of, so R1 depends on what? R1 depends on NR and AA. Okay, so what is the membership value of NR for X, and what is the membership value of AA for Y? Okay, so if you find here, if you check out here, so this we have calculated. Okay, what is the membership value for NR with X? For AR with Y? Yeah, so like this we have to map. Okay, so we have only 4 combinations. Okay, NRAA means, so NRAA, let us here itself find the rule strength. Okay, so we have totally 4 combination of rules possible. So if it is NR AA, if it is NRAA, say let me write like this, NR AA. Okay, then you have to find the minimum of NR and AA. So NR is what? 0.6571 and AA is 0.333. So what is the minimum? 0.333. This is the strength. This is the strength of this rule. So let us call it is R1. Okay, R2, if you take, it is NR and AR. So what is NR and AR? Again 0.6571 into 0.6667. What is the minimum? 6571. This is the strength of this rule, rule 2. If you see rule 3, it is FR and AA. Okay, so FR and AA, which is nothing but minimum of, what is FR? 0.3429 and 0.333. What is the minimum? Yeah. Similarly, rule 4. Rule 4 is what? FR in FR and AR. So which is nothing but the minimum of 0.3429 and 0.666, 36 and 7. So what is the minimum? 0.333. 3429. Okay, right? So here the first two rules. So from here you can see which rules has the minimum strength. Which rules? So there are two, this is the strength of each rule. R1, yeah, R1 and R3 is the strength is minimum. So you can reject these two rules. You can reject these two rules. Okay. So whichever the rule strength is maximum, that we will take. Okay. We will take only these two rules, R2 and R4. So that is what we are doing next. Okay. So we are calculating the rule strength for R1, R2, R3 and R4. So as a result, you can see that the strength of R1 and R3 were less. So we are going to reject these two rules. We will consider only these two rules. Okay, which has a better strength, right? So finally, we are taking only uh, two rules. Okay. The next step is to determine the fussified outputs corresponding to the each rules. Okay. So the working principle of doing this is first discussed. So first we will discuss how to. So we have identified some two rules. From these two rules, we are going to decide like what is the angle of deviation the robot should take. Okay. But before going to the actual process, let us discuss how this technique is going to work. Okay. So we are going to discuss just a process. We are stopping the problem there because we are going to discuss like how this further we are going to work out, right? With an example, right? Suppose consider there are two rules, R1 and R2, right? Which are used to decide on fuzzy output. R1 is given something like this. If S1 is A and S2 is B, then F is C1. Okay. So see this two rules means what? Two rules are two different situations. So now we have ignored two rules, but there are two rules. This rule is talking about one situation. This rule is talking about another situation. This rule is talking about the case of near and ahead right. That is, if the object is near and ahead right, then do this. This is what this rule says. And this rule says that if the object is far and ahead right, then do this. This is what this rule says. Okay. So the same thing here we are taking as a generic form. If S1 is A1 and S2 is B1, then F is C1. Do this, right? If S1 is A2 and S2 is B2, then F is C2. Then do this. Okay. So suppose S1 and S2 are the inputs of the fuzzy variable S1 and S2. It is S1 star and S2 star are the input for the fuzzy variable S1 and S2. And mu A1, mu A2, mu B1, mu B2, mu C1 and mu C2 are the membership values for different fuzzy sets. Okay. A1, A2, B1, B2, C1, C2 are the fuzzy sets. Let us assume mu A1, mu B1, mu B2, mu C1 and mu C2 are the membership functions for all these fuzzy sets. Okay, then the fuzzy output what we are going to take is, see there are two rules here. First rule says that if S1 is A1 and S2 is B1, then F is C1. Okay. Second rule says that if S1 is A2 and S2 is B2, then F is C2, right? Okay. So let us assume the input is S1 star. Okay. And there are two inputs, one for first variable, that is one for S1 and another one for S2. Okay. So S1 and S2 is coming in both the rules. Okay. So one is S1. So the input for S1 is S1 star, and the input for S2 is S2 star. Okay. Right. So this is the membership function corresponding to A1, right? And this is the membership function corresponding to B1, and this is the membership function corresponding to C1. Okay. Similarly, this is the membership function corresponding to A2. This is basically for rule 1. This is for rule 2. Okay. This is the membership function corresponding to A2. This is the membership function corresponding to B2, and this is the membership function corresponding to C2. Right. So these are the inputs, S1 star and S2 star. So if you draw the line on S1, a perpendicular line, you see it is intersecting at some point on the membership function of A1 and A2. Okay, right? Similarly, if you draw a perpendicular line on S2 star, it is intercepting at some point on the membership function B1 and B2. Okay, fine. Now this C1, how we are going to decide in the sense. So again whatever the point at which S1 star and S2 star hitted in the membership function A1 and A2, there you draw a horizontal line towards the membership function of C1. Okay, but we will take only the minimum of that. So here there are two lines. This is the maximum one and this is the minimum. So we take only the minimum area, right? Similarly, do this for the second rule also. The second rule also, this S1 star, wherever it is hitting on the membership function A2, draw a horizontal line. Similarly, wherever S2 star is hitting, there also draw a horizontal line. Okay, and now also here also you take the minimum one, right? Okay, so that is from C1 we are going to consider only this part. Okay, and from C2 we are going to consider only this part. Now just merge these two things, combine these two things. That is, we are going to take a union of C1 and C2, but not the full union. See, the full C1 is this, but we are not taking the full C1. So out of these two things, whichever the minimum part of that only we are taking. Similarly, here also we are taking the minimum part. So that is the final result. Okay, so this is how we are going to calculate the result, right? This same operation we have to do for our inputs also. Okay, so in our case, S1 star is what, 1.04, S2 star is what, 30 degree. Okay, and what are the things we have? We have near one membership function for near, one membership function for ahead right, one membership function for far, one membership function for ahead right. Okay, and if it is near and ahead right, then what is the result? For that we have a membership function. If it is far and ahead right, what is the resultant deviation should be taken? For that there is a membership function. So all these things we have to plot, and we have to take for each of these membership function we have to take the minimum one and we have to merge it. So that's what we are going to do. Okay, so I think it's clear. So actually here, yeah, so we have to consider only two things. So it is enough if we consider only two rules, but actually here we are considering all the four rules. So initially we have discussed that two rules can be rejected, right? Two rules can be rejected because of less strength, but for this exercise all these four rules were considered: R1, R2, R3 and R4. That is, so initially we had four combinations, right? Near and AA. Then in that case the robot will take a right turn. It will go towards the right. Okay, it will deviate towards right. Okay, so that is specified by this membership function. Okay, so the second case is near and ahead right. In that case the robot will go ahead. Okay, the third case is far. So these two cases are far and ahead. In this case the the robot will take ahead right. The fourth case is far and ahead right. In this case the robot will go ahead. Okay, so these are the inputs: d 1.04, theta 30 degree. So just to draw a vertical line and see where it is hitting on all these membership function. Similarly 30 degree, you see where it is hitting on all these membership function. Okay, now draw a horizontal line. Now this is the resultant, the membership function. Here we will take only this part. Okay, similarly here it is hitting in these two places. In this one also we will take only this minimum part, right? Similarly the third one, the whatever the minimum, whatever the one with a lesser value, that only we will take. Okay, this one we will take. Similarly in the fourth one we will take only this part, right? Now you merge all these things. Now we merge all these things. Okay, so if you merge all these things you will get something like this, right? Okay. Okay, so after merging all these things, now we can find the what do you call, uh, so this is something like, in defalsification we have discussed, no, the center of sum method. Now you can apply the center of sum method to find the actual output, that is the actual angle of deviation. So here we are using center of sum method. So center of sum method is nothing but, see, this everything can be considered as a trapezoid. So this is one trapezoid, this is one trapezoid, this is one trapezoid. So we can find the area of this trapezoid, 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 and take the midpoint. So if this midpoint is C1, then C1 into A1, C2 into A2, C3 into A3, C, this is C3, C4 into A4, that will come in the numerator. Add all these things, C1 into A1 plus C2 into A2 plus C3 into A3 plus C4 into A4 divided by all the areas A1, A2, A3, A4. Okay. So like that, if you calculate, this is the value you will get, right? Actually in this figure these numbers were not clear, so we cannot calculate exactly, but this is the overall logic, right? So now what we can conclude in the sense, this is the angle of deviation the robot should take to avoid collision. Okay, right? I think this is clear. So this is how the Mamdani's model work, right? If you have any doubts, you can ask. Otherwise, we'll move to the next technique. Okay. So the next technique is called as Takagi and Sugeno's approach. So basically we are discussing about what? Fuzzy logic controller. How to build a fuzzy logic controller. So one of the method to build a fuzzy logic controller is Mamdani approach. Okay, Mamdani approach is highly interpretable but is less accurate. Takagi and Sugeno's approach is more accurate but is less interpretable, right? Okay. So here also we use, as usual, we use rule based. So a rule will have antecedent and a consequent part, that is, if this happens then that will happen, something like this. Okay. So any rule, if it is any rule, any ith rule is represented like this, that is, if x1 is a1 I represents the rule number. If x1 is a1 x2 is a2 x3 is a2 so on and so forth, and xn is an then the output is given like this, y output. Okay, yi, that is the output of ith input is a0 I plus a1 I x1 plus a2 I x2 so on and so forth, an I xn. Okay, where this x1 x2 x3 up to xn is coming directly from the input. Okay, because it is in the input itself, in the input rule itself. Okay, these a0 a1 a2 an, these are the coefficients, these are called as coefficients. Actually this identifying this coefficient is a tricky thing. So this is one of the crucial job of the engineer who decides this Takagi and Sugeno's approach. Okay, I don't think there is any logic to identify these coefficients. It is something like an maybe based on experience or based on some error and trial method, this coefficient should be identified appropriately so that the model will work in a better way, right? Okay. Apart from this, we should also find weight. The weight of the ith rule can be determined for a set of inputs x1, x2 and xn. So if there are inputs like x1 up to xn, then the weights of these inputs can be identified something like this. So weight of ith rule is nothing but the membership value of x1 into membership value of x2 into membership value of so on and so forth up to xn. Okay, so all the membership values were multiplied and then you are getting the weight. Okay, it then finally, to get the output, what we do is, so we need two things. One is we need y and the other one is weights we need. Okay, So then to finally to get the output, we apply this formula. Y is equal to sigma I to k wi yi divided by wi, right? So see, this is the overall thing we are discussing, like how this Takagi and Sugeno's approach work, right? So you just try to understand that there are two things we have to identify. One is we have to identify the weights, which is called as wi. Other one is we have to identify yi. Okay, yi is normally it's something like a guessed value. These two things we have to identify. Okay, for for all the possible uh, cases, right? Then once you identified all these things, you have to plug into the formula. Sigma I equal to 1 to k wi yi divided by wi, right? So this is what we are going to do. Okay? I think it's clear. So initially we will be given set of rules. These are the rules. X1 A1, X1 is A1, X2 is A2, so on and so forth up to Xn is An. Okay. From this first we have to identify yi. So how you identify yi? Yi is nothing but A0 plus A1 X1 plus A2 X2 plus An Xn. Again this A0, A1, A2, A3 are the coefficients. Okay. So based on this correctly predicting these values, we will identify y. Okay. Then we have to calculate wi. Wi is nothing but by taking the product of all the membership value of given x1, x2 up to xn, right? Once we got the all wi's and yi's, then we have to plug into this formula, right? Okay. So in Mamdani's approach, Mamdani approach uses what is called linguistic variables to define possible values, right? But Takagi and Sugeno's approach, it does not use a linguistic variables. It uses some mathematical equations. Okay, this yi, all these are mathematical equation. So rather than linguistic elements, it uses mathematical equations. Okay, fine. So let us discuss with an example. So consider two inputs, I1 and I2. Let us assume there are two inputs, I1 and I2. Say that I1 takes these values. These are the possible values I1 can take: low, medium and high. Where low is represented as, can be represented as L, medium as M and high as H. And I2, these are the linguistic values it can take: near, far and very far. Okay. Now see, that means you have two, these are the inputs. Okay, these are the inputs. Now you have to find the output. Okay, now this, how many combinations of these inputs are possible? How many combination of these inputs are possible? I mean, yeah, 9 combination. If if I1 is low, then I2 can be either near, far or very far. If I1 is medium, then I2 can be either near, far or very far. Okay, if I3 is, if I1 is high, then I2 can be either near, far or very far. So like that, there are what you call, there are 9 combinations are possible. This can be again represented through a matrix. So this is low, medium and high. It can take either near, far or very far. Okay. Now these are linguistic variables only. That is fine. But in the previous discussion, we said that Takego and Sugeno's approach does not use a linguistic notations. That is for the rule. For rule, it won't use linguistic notation. This is for input. For input, it takes linguistic notation. Okay, this is input. That is, if it is low and near, if the input is low and near, then what should be done? So this will not be linguistic. This what should be done will not be linguistic. Whereas in Mamdani approach, this also will take a linguistic form. Okay, if the input is, if the input is low and far, then what should be done? If the input is low and very far, then what should be done? If the input is medium and near, then what should be done? So all these things will not, these actions will not be of linguistic notation. Rather, it will be some mathematical equation. So what it will be here in the sense, some mathematical equation. So this is what we call as y1, y2, y3. So we'll have, like, we'll have 9 equations, y1, y2 up to y9. So these are represented through some mathematical equations, right? So okay, So the output of an ith rule can be expressed by the following. That is, so as I said here, ith rule, that is, it is a ith rule is a function of I1 comma I2. Ith rule is a function of I1 comma I2, right? So every rule is a function of I1 and I2 only, where I1 can take value between low, medium and high, and I2 will take value between near, far and very far. Okay, but to this, so this function of I1 and I2 function means what? Again, to this we will add some parameters. So these parameters are Aj and Ak. Aj and Ak. So it is Aj, you can say it as Aj I1 plus Bk I2. Okay. Okay, this I represents ith rule. For ith rule, the ith output, right? So where J and K can take, so this is our assumption. This can be anything. So this is what I said. This is actually, this J and K values, all these things will be decided by the designer of the Takeko-Subinus approach. So it is actually, these numbers are fixed by experience. Okay, there is no general rule for that. So here let us assume that this J and K can take values 1, 2, 3. Okay. For example, if J is 1 and K is 2, then in this case it will be A1 I1 plus B2 I2, something like that, right? Okay. Or suppose A1 equal to 1 and A2 is equal to 2 and A3 is equal to 3. Okay. If I1 is equal to L, M and H respectively, and B1 equal to 1, B2 equal to 2 and B3 equal to 3, if I2 is equal to N2, FR and VF respectively. Okay, that is we are fixing, that that A1 will be always 1, A2 will be always 2 and A3 will be always 3, and B1 will be always 1, B2 will be always 2 and B3 will be always 3. Okay, so now let us calculate, if I1 is given as 6 and I2 is given as 2.2, I1 is given as 6.0 and I2 is given as 2.2, then what will be the output using Takeko and Sugeno's approach? So this is the what you call the distribution of I1 and I2 using fuzzy membership function. It is represented, that is, this represents low, okay, and this represents medium and this represents high. Similarly, this represents near, this represents far and this represents very far. Okay, now again we have to use the same technique like how we followed for initially, how we followed for what you call Mamdani's approach. Here you can see I1 is 6.0, I2 is 2.2, right? I2 is 2.2, right? So see here, if you want, I'll write here, this is LMH, okay, LMH, and this is near, far, very far. Okay, so this will be L and near means is Y1, okay, this is Y2, this is Y3, Y4, Y5, Y6, Y7, Y8 and Y9, right? So there are some parameters. Okay, we have some parameters for L, M and H. Okay, the parameters for L, M, H are A1, A2, A3. So for L we have A1, this for A2, this for A3. Okay, for near, far and very far we have parameters B1, B2 and B3. Okay, so yi is given as what? Yi is given as Aj L1 plus Bk L2. Okay, so but we are assuming what? A1 is always 1, A2 is always 2, A3 is always 3, B1 is always 1, B2 is always 2, B3 is always 3. So Y1 will be uh, this is Y1 is connected with A1 and B1. Okay, so A1 L1 plus plus B1 L2, right? What is A1? A1 will be always 1 and B1 will be always 2. Sorry, A1 will be always 1 and B1 will be also always 1. So it will be nothing but L1 plus L2. Okay, this is for Y1. Similarly, we have to calculate for Y2, it is A1 and B2. Okay, so it is A1 L1 plus B2 L2. A1 will be 1 whereas B2 will be 2. So it will be L1 plus 2L2, right? Similarly, if you see for Y3, it will be A1 and B3. So it is A1 L1 plus B3 L2. Okay, A1 is 1, B3 is 3. So it is L1 plus 3 L2. Okay. So like this, these rules were framed. We will use this towards the end so that I am clarifying, right? Okay. So could someone say what is Y8? Y8 will be what? Y8 is connected with what? A3 and B2. So what is that? Yes. L2. What is A3? 3. So 3L1 plus what is B2? 2L2. Okay, this is how we form this. Now how this 1, 2, 3 comes means that is given. Okay, so that actually the designer of the model, based on his experience, he fixed these values, right? Okay. Now in our case, this is the input. L1 is 6.0, L2 is 2.2. Okay, so we have to, so these are the 9 rules totally. So the system contains 9 rules, but all these 9 rules may not fire. So any of these few rules may fire. So which are the rules are applicable, that we have to find out. So for that we have to plug this 6.0 and 2.2 into the membership function. Okay, so L1 is 6.0. Okay, L1 is 6.0, and so L1 corresponds to this this thing, low, medium and high, and L2 corresponds to near, far and very far. Okay, so 6.0, where it will come, this is 5, this is 10, so this point is maybe 7.5, so 6 will come somewhere here. Okay, so 6.5, it is connected with which membership functions? Yeah, it has some membership value for medium. Okay, and also it has some membership value for low. Okay, so it has some membership value for medium and also it has some membership value for low. Okay, so it comes in these two cases. Similarly, L2, so this is the plot for the membership function for L1. For L2, what is the value? 2.2. L2 is 2.2. So again, if you see 2.2, this is 2 and this is 3. So 2.5 is somewhere here. So 2.2 should be somewhere here. Okay. So this 2.2. So if L2 is 2.2, it is connected with which membership functions? Yeah, it is connected with far and very far, with some membership value. Okay. So 2.2 is connected with far and very far. Okay, this is connected with medium, low and medium. This is connected with far and very far. Okay, so low, medium, far and very far. Okay, right? So what are the possible rules it may fire? These are the rules it may fire. Okay, these are the combinations. How many combinations here we have? Again, four combinations: low and for, low and very for, medium and for, or medium and very for. Okay, so this is low and for, low and very for, medium and for, medium and very for. So these are the four possibilities we have: y2, y3, y5 and y6. Okay, right. So the input I1 equal to 6.0 can be called either L or M. So that's what we have discussed in the previous slide. Similarly, the input I2 equal to 2.2 can be declared either F or a VF. So again, using the principle of similarity of triangle, we have to find the values. Again, you have to use the principle of similarity of triangle. Okay. So for example, how will you find this? Say this point. Say I want to find this point. How will you find this point? So if you want to find this point, this is the one we want to find. Okay. So then this is one triangle. Okay, and this is another triangle, right? So this is x and this is y. Okay, y is 1. So x by 1 is equal to what? This is this part is so this is what? 6.0. This is 6.0, right? Okay. So this is delta 1, right? This is delta 1 and this entire thing is delta 2. So 5 to 6, the distance is what? 6 minus 5 is 1. Okay. And 10 minus 5 is, so it is for 0.8. Okay. So this is 6.0. Okay, maybe we have to do reversely. This is, assume this is delta 1, this entire thing is delta 2. If this is delta 1, then what is the distance? 10 minus 6 is 4, right? So this is delta 1. Okay, 4 by 5. What is 4 by 5? 0.8. Yes. So that is how we got this 0.8, right? Similarly, similarly you can find for the other points, right? Similarly, this point, if you take this point, so this is 6.0. So if you draw a line, it comes here, right? So this is one triangle. Okay. This is another triangle, right? This is 6.0. Okay. So again, x by, this is 1, this is y, equal to delta 1. Now what is delta 1? I think this is delta 1, right? So this end is delta 1 and this is delta 2. Okay. So it is 6 minus 5 is 1 by, I think it is 1 by 4, right? Yeah. 6 minus 5 is 1 and this is 10 minus 6, it is 4, 1 by 4. I think it is 0.25, right? So similarly you can calculate for this also, right? So that is how we got this value. So mu L of L1 is 0.8, mu M of L1 is 0.2, mu F4 of L2 is 0.8, mu VF of L2 is 0.2, right? Okay. So these are the 4 rules that can fire. That is, if L1 is L and L2 is F4. Okay, so that are the 4 cases possible, right? Because here it can take what? L and M, and here it can take F4 and VF, right? So L, M, F4, VF. These are the 4 cases possible. So rule 1 is I1 is L and I2 is F4. Rule 2 is I1 is L and I2 is VF. Rule 3 is I1 is M and I2 is F4. And rule 4 is I1 is M and I2 is VF, right? So these are the 4 cases we have. Now we have to find the weights. Okay, so here yeah, we have to find the weights for each of the rule. So what we are doing in the sense, in the previous case we have find what uh, we have found the minimum, right? We have taken the minimum of two things. Okay, but here what we are doing is we are not following that approach. Weight 1 is nothing but it is the membership value of, see, rule 1 is corresponding with what? It is corresponding with L and F4. Okay, so what is the membership value for L? 0.8. And what is the membership value for F4? It is, this is also 0.8. Okay, right? So you just multiply these two things. 0.8 into 0.8, it is 0.64. Okay, this is the rule strength of R1. R2, it is what? It is L into VF. So what is the membership value for L? L is 0.8. Okay, right? So see, here itself we can calculate the rule strength of R1. R1, it is nothing but L into F4. So L into F4 is 0.8 into 0.8, which is 0.6. Okay, what is R2? R2 is connected with which one? L and VF. What is the membership value for L? 0.2. What is that? 0.16. And R3, it is connected with what? M and F4. What is the score for M? Yeah, what is that? Similarly for R4, what is it connected with? M and VF. What is its score? Yeah, which is nothing but 0.4 or 0.04. 0.2. Okay, I think this calculation is wrong. It's not 0.6, right? 0.2 into 0.2. It's 0.04. Okay, this should be 0.04, right? This is M into VF. What is VF? VF is 0.2. Okay, right? So this is 0.04, right? So right, and then the functional consequent for each rule. So the rules are y1, y2, y3 and y4. Okay, so actually here you can see what are the rules that will fire in the sense. So these are the rules. Actually it is y2, y3, y5 and y6, right? So y2 is connected with what? Y2 is connected with what? Which parameters? A1 and B2, right? A1, so it is A1 L1 plus B2 L2. Okay, what is A1 value? A1 value is 1, so it will L1 plus 2 L2. Okay, so you can see here the first rule is what? L1 plus 2 L2, right? The second rule, if you see, it is y3. Y3 is connected with what? So A1 L1 plus B3 L3. A1 is what? 1. So B3 is what? 3. So L1 plus 3 plus 3 L2 is L2. Okay, so second rule you can see it is L1 plus 3 L2, right? That is how we got this. Similarly, if you see the third rule here, y5 is connected with what? A2 L1 plus A2 and B2. It is connected with A2 and B2, right? Here A2 and here B2. Okay, So this is A2 L1 plus B2 L2. What is A2? 2. 2L1. What is B2? 2. 2L2. 2L1 plus 2L2. Okay, 2L1 plus 2L2, right? Similarly, the last rule. What is the last rule? Last rule is Y6. It is connected with what? A2L1 plus B3 B3L2. These two are always L1 and L2. What is A2? 2L1 plus B3, 2L1 plus 3L2. Okay. So that is how you got this thing here, 2L1 plus 3L2. Okay. Now we have all these things. What is L1? L1 is given 6.0. What is L2? 2.2. Fix up. So just if you plug it, you will get all the values. So this is Y1, this is Y2, this is Y3, Y4. So now we got W1, all W1 and all Y1. So what is the formula you recall? Sigma Wi Yi, okay, divided by sigma Wi, right? So that is what next we have to do. So what is Wi, W, that is 0.6 into 10.4. So all these things you just calculate, right? So it is 0.6 into Y1 is what? 10.4 plus 0.16 into 12.6 plus 0.16 into 16.4. This you calculate. Maybe some mistakes may be there. I'm not sure. Plus 0.04 into 18.6 divided by sum of all weights. These things. Okay. That is 0.6 plus 0.16 plus 0.16 plus 0.04. This is 0.04, right? So that is the final result. Okay. So this is the actual output. So this is what the controller is expected to do, right? So this is how this Sugano's approach works, right? Fine. Let us stop here for this session.